Hey everyone, and welcome. Today we are diving into one of the absolute cornerstones of organic chemistry, electrophilic aromatic substitution. We're going to break down how it works, why it even happens, and best of all, how you can use it to build some really cool complex molecules starting with plain old benzene.
All right, so let's jump right in. We all know benzene, right? It's got this perfect, super stable cloud of pi electrons. It's kind of happy just the way it is. So the big puzzle for chemists has always been, how do you break into this super exclusive, stable club and actually get it to do some chemistry? That is the fundamental question we're going to answer today.
The answer, it turns out, is a very special kind of reaction. It has to be something powerful enough to tempt benzene out of that aromatic comfort zone. And this is the fundamental way chemists can take a benzene ring and start turning it into all sorts of useful compounds, from medicines to materials.
Okay, so the name itself, electrophilic aromatic substitution, sounds a little intimidating, I get it. But let's just break it down. Aromatic, well, that's our benzene ring. Electrophilic means we're using an electron lover, some molecule that's really craving electrons. And substitution is the key part. We're not adding anything permanently, we're doing a swap. We're replacing one of the hydrogens on the ring with our new electrophile.
So really, here's the entire idea in a nutshell. You've got your electron-rich aromatic ring. That's our nucleophile. And you bring in a really strong electrophile, our electron lover. The ring's electrons see that electrophile, they're attracted to it, and boom, they make a swap, kicking out a proton in the process just so the ring can get its precious stability back. Let's walk through exactly how this happens step by step. First up is the attack. That cloud of pi electrons in the benzene ring literally reaches out and grabs onto the strong electrophile. Now this is the hardest part of the whole reaction, because for a split second, we break that beautiful, stable aromatic system. This creates our intermediate, which is step 2. We form a carbocation known as an iridium ion. Now this thing can exist because that positive charge isn't just stuck on one carbon. It gets passed around the ring through resonance. It's shared, which makes the whole thing just stable enough to hang on. And finally, the payoff. A base comes along, plucks off a proton from the same carbon that was attacked, and those electrons snap right back into the ring. Aromaticity is restored, and the substitution is complete.
Okay, but this is where it gets really interesting. What happens if benzene already has a group attached to it? Well, that group doesn't just sit there and watch. It takes charge. It basically acts like a movie director, pointing and telling the next incoming group exactly where it's allowed to sit on the ring. And these seats all have names relative to our director, that first group. The spots right next door, those are the ortho positions. The one directly across the ring, that's the para position. And the two in between are called the meta positions. That director group will guide the new electrophile to one of these specific spots. And if you look at the different kinds of directors, you'll see two really clear patterns. We can sort them into groups that activate, meaning they speed up the reaction, and groups that deactivate or slow it down. Now look at the trend. See it? All the activating groups are ortho/para directors, and almost all of the deactivating groups are meta directors. And then you've got the halogens. They're the weirdos of the group. They actually slow the reaction down, but they still direct to the ortho and para positions. We'll get to why in a bit. So we've seen what happens. But now for the fun part. Why does it happen? Why do these groups direct the way they do? Well, it's not magic. It's all about electronics and stability. We just have to follow the electrons. And the secret is right here. It all comes back to that aromatic ion, that carbocation intermediate we just talked about. The directing group on the ring has a huge effect on the stability of that intermediate. The more stable the intermediate, the faster it forms. And in chemistry, the fastest path is the one the reaction is always going to take. So let's take an activating group, like a hydroxyl group, an OH. When the electrophile attacks at the ortho or para position, that positive charge gets passed around the ring, and eventually it lands right on the carbon that's attached to the oxygen. And this is huge, because the oxygen can use one of its lone pairs to form a double bond, creating an extra super stable resonance structure where every single atom has a full octet of electrons. That is the holy grail of stability. Now, if the attack happens at the meta position, the positive charge never lands where the oxygen can help out, so that pathway is way less stable, and the reaction just avoids it. Now, what about a deactivator, like a nitro group, minus NO2? This group is yanking electron density away from the ring. So, if an attack happens at the ortho or para position, one of the resonance structures puts the ring's positive charge right next to the already partially positive nitrogen in the nitro group.
That's a huge no-no. Two positive charges side by side, they repel like crazy, making that intermediate incredibly unstable. The reaction will avoid that path at all costs. The meta position is the only one that keeps that positive charge away from the nitro group. It's not a great option, mind you, but it is the least bad option available.
Okay, so now we have the rules of the game. We know how to add one group, and we know how an existing group directs the next one. So let's put on our molecular architect hats and see how we can use these rules to strategically build a specific molecule.
So here's our challenge. We want to make this molecule, 3-chloroaniline. Now, take a look at the relationship between the two groups. They're meta to each other. But wait a minute. If we look back at our chart, both the amino group and the chlorine are orthopara directors. So how in the world did we get them to sit in a meta arrangement? This seems impossible. The way to solve puzzles like this is with a super powerful technique called retrosynthesis. Instead of just guessing the first step and hoping for the best, we start with our final product, and we work our way backwards, one step at a time, until we get to a simple starting material like benzene. Okay, let's try it. We start at the end with 3-chloroaniline. We know that NH2 group is an ortho/para director, so it absolutely could not have been on the ring when the chlorine was added. But we know a trick. We know we can make an amino group, an NH2, by reducing a nitro group, an NO2. And what kind of director is a nitro group? It's a meta-director. Aha! That's the light bulb moment. That means the molecule we had right before our final product must have been M-chloronitrobenzene. Okay, so how do we make that? Well, that's easy now. We start with nitrobenzene, and since the nitro group is a meta-director, it will force the chlorine to add at the meta position. And of course, we make nitrobenzene from benzene. We've solved it. We figured out the path by going backwards. So now let's just lay it all out in the forward direction. It's this elegant three-step synthesis. Step 1, we nitrate benzene to make nitrobenzene. Step 2, we chlorinate our nitrobenzene. The powerful meta-directing nitro group does its job and forces that chlorine right where we want it. And finally, step 3, we just reduce the nitro group to our target amino group, and voila, we have successfully built 3-chloroaniline. And that's really the key takeaway. When you understand these directing effects, you're not just a person mixing chemicals anymore. You're a molecular designer. You can strategically and logically plan out how to build molecules with precise structures. The possibilities are pretty much endless. So the only question left is, what will you build next?